So this is work in collaboration with Kaho, who is actually sitting right here, and Zhaoming Gan is a research scientist that I work with, and Xiang Fu and Hui Rong. And we have a couple of papers that's published, and there's one under review. There's a couple more we're writing if we can get our act together, finish them. I noticed there's our space colleagues. So they actually measure reality in a way, in the sense that they can have in situ measurements, maybe even multi-point measurements, where this beautiful solar wind turbulence. And I want to advertise some of the papers that one of the meeting organizers, Xiao, and I wrote. We write one paper a year, so the last 2 years. It turns out Voyager actually have in situ measurements, very local interstellar medium. And there was actually an interesting topic whether the fluctuation they measure with the color black curve here is due to the cascade of the ISM turbulence that we've been talking about. It turns out there are serious doubts that's the case. And it's a partially ionized medium. One of the things we emphasize that ion neutral damping actually cuts things off way earlier than that. So this is might very well be local in origin, right around the heliopause. So it's a very interesting topic, at least maybe for the helio physics. And then we heard lots of talks on all this interstellar medium, galaxy, CGM, and ICM. I also want to, Betty mentioned this, this is a fascinating talk, SS433, the galactic jet, and we now have multi-wavelengths. This E1 region, which is seen by Hawk in tens of TeV, and LASSO saw up to 100 TeV, and saw changes in 10-ish TeV, and an X-ray optical, and XP saw polarized X-ray emission from the same region, implying very large-scale magnetic fields. And if you do spectral modeling, if it's a leptonic model, that's a big if. The energy goes up to about PeV. PeV electrons in our own backyard. So there's, and those particles, their gyro radius is about, maybe 1/100th of the region you actually see in the telescope. So you do worry about their acceleration as well as transport. And they probably see all kinds of curvature and bends and turbulence that's can be actually measured by optical and radio along with the X-ray. So one of the things I kind of want to go back to what Martin mentioned is, this is very naive, very basic question. When you do turbulence simulation, we measure turbulence. When I was in grad school, which I won't tell you how many years ago, the simple thing was, let's just add up all the MHD waves, the Arfin modes, the eigenmode, the slow modes and fast modes. Then I graduated, thankfully, in the GS95, published. And I was in a meeting filled with space physicists, and so I asked them this question: can I treat turbulence as ensemble waves, or there's something fundamentally just wrong with that? And I was told, go read all the papers about 2D plus lab. For those who don't know the terminology, that's okay. But this is one of the dominant models, still maybe the dominant model. Greg probably disagree, but in the space physics community, they have in situ data, and they analyze them, they present them, they look like two big components, that's 2D-like, and then plus parallel. There's actually, this question stuck with me for almost 30 years, and it turns out there are ways of analyzing them, right? So I apologize for those. It sounds like going back to graduate school courses, but there's Arfin waves and the slow and fast modes, and we were all carefully taught they have very good dispersion relations. You gave a K parallel, K perp, or K value, and gave a beta, plasma beta. You know what the frequency of that oscillation would be, and you plot them on this omega versus K parallel, K perp 3D domain. They appear as dots. And for continuum, they actually lie on surfaces, and our thin surfaces, the slope is our thin speed, that's a sheet. Fast and slow actually are slightly warped depending on the beta. So very naively we say, okay, so why even worry about frequency? Many of us have heard talks about bending, what else? Curvature. You know, okay, come on. Why worry about frequency? Okay, so, right, so really, underneath all this, there's something called quasi-linear theory of Fokker-Planck equation. So you have all the particles moving all the random, in all the fluctuations. If you say, how does the pitch angle vary? Is this kind of correlation function separated by time, right? So, and then, what is? Okay, so, and this is a general resonance condition where you do want to know the frequency of the fluctuation, the wavelengths in the parallel direction of particle speed and gyro frequency. That's the very basic idea. And the more general terms you write for any correlation function, you can write it in this transform form, and then the spatial function, which, for example, in astro community, we'll use, say, Goresh radar model for the spatial K information, and K parallel, K perp. And there's actually a time decorrelation. The physics idea is the fluctuations over some time will decorrelate, and you don't want to do things beyond. You need to know how it decorrelates so that when the energies, when the time is taking longer to be that, and this information is encoded in your correlation function. So there's something wrong with my laptop. It won't go. So the brute force way, which is what we took, is to say, okay, we run MHD turbulence driven turbulence isothermal simulation for a long time, let's say many eddy turnover time, and we just save the data cubes very frequently. And so then you have this quantity, say density or velocity fluctuation, and you can think of them, decompose them both in spatial time and in omega, and that gives you the 4D FFT spectra. So you get frequency as a function of spatial variation, and then you just look at them, right? So, and this is what we see. So again, this is frequency, and you see the driving, shows up in all frequency, this K parallel, K perp. So those are the three isosurfaces. You do see modes kind of go along some of those surfaces, but this is logarithmic scale. You can't see the scale here. This is a 10 to the 9, this is a 10 to the 1. And majority of them lying in this very low frequency, omega 0-ish, large K perp plane, and with some K parallel. So, and if you do cuts, right? So then you recover the textbook solutions, the fast mode, Arfin modes, and slow mode, except this gigantic region is filled with low frequency fluctuation. And in this K perp plane, where you only get fast modes, and you have all this energy that's not explained by eigenfunctions. And this kind of 4D FFT approach, we're not the first one to do it. I mean, some of the space community folks have been doing this, and other community have been doing this for the past decade also. Now, how do we understand that low frequency behavior? And then the second part of the talk is I want to draw some implications. One of the ideas, so the way we try to come up with the model is to say, okay, this is a nonlinear, must due to nonlinear interaction. Otherwise, you solve this linearized equation, you should get all the power follow those isosurfaces, right? So, and all the nonlinear terms, we made a heuristic assumption. This is the strong assumption. We say all the nonlinear terms goes some nonlinear frequency as a function of K vector. And this, we're going to treat as a variable that can change for Arfin modes, fast mode, slow mode. We don't assume the functional form. We don't assume what it should be in terms of different wave modes. And then by substituting that into this equation, and then you can actually solve it, get the, say, velocity variation power. It turns out it has a nice functional form. It's Lorentzian-like, but it's not quite the clean Lorentzian that we learned in the damped harmonic oscillator in freshman physics. But this omega nonlinear function shows up in places, and then you do have the resonance-like. This is the eigenwave function. So turns out this gives what I consider, I was shocked when when Kaho showed the fitting. He made, I don't know, tens of million hour runs, used up a lot of Los Alamos computer time, and for different Mach number, different beta, high beta, low beta, and we had compressor driving, you name it. So, but basically the fitting we were able to get is that for this particular case, sonic Mach number is 0.9, our thing is 0.1, beta is 0.1, 0.2, sorry, and then this is omega, this is the power, and we separate them into slow, Rfin, and fast. Each of those peaks are the eigenfrequency you would expect for this particular K parallel. And then you can see the width is different for different modes, and then we can just fit it, and then we run as a function of K perp, and then we can gradually get the fitting for the omega nonlinear. So that's one of the goals, to figure out, due to this nonlinear interaction, how is the omega nonlinear varies for different wave modes as a function of K parallel, K perp. And so that's what this paper that's on the archive and on the review was mainly about, is to describe this model in detail and present the fitting. And for low beta, it turns out for K parallel equals 0 mode and K perp finite, the frequency power is dominated by slow and Rfin, and then you do get the fast mode peak here, and then for the finite K parallel, K perp, you get this broadened Lorentzian looking function that I presented earlier, and all the lines are the functional fitting, and the dots are from the data simulation analysis. So given the limited time, I've just used one case where beta is 2 here, and we fix the K parallel, and then we get omega nonlinear function of K perp. In this case, for Rfin slow modes, that's the red and blue dots here. This slope is it's reasonably fitted by K perp to the 2/3 power. For those who are familiar with the GS95 model, this is kind of the scaling you would expect. And for the fast mode, it's either 1 or 3/4. It's 3/4 maybe has a slightly better fitting, and that's we have implications for the other type of turbulence model. And just going back to the 4D plot I presented earlier, that the very low frequency dominance turns out all coming from very small low K modes that has K parallel equals 0 and finite K perp. So the K perp 3, 4, 5 modes are the ones that this thick black curve is the summation that dominated the whole power. Okay, so some implications. So it turns out if you really stare at this Lorentzian function that we got, it has 4 roots, plus minus omega wave, which we call omega A here, and then the omega nonlinear, which is separated into the omega wave plus omega nonlinear, and you put this back into the time decorrelation function that I was mentioning earlier. So the gyro resonance idea is often assumed resonance, so delta is at wave, so that's the delta function, and then there are in the literature there are models to say, okay, the time decorrelation is actually Gaussian looking, so that's one of the functions, and then you can also propose a simple Lorentzian just by adding a constant damping term, and then those are the blue and red curves here. the green dashed curve is using our model. Is actually, you do see they return some of the features that recognizing there is the eigenwave, but it's a lot broader and also has a high power at low frequency, which is one of the key findings. So this new time decorrelation function that kind of derived fitted from the data does show a significant difference from some of the other models used in the literature. And the implication of this that we've been talking about cosmic ray transport. So this is the time-related, frequency-related function in calculating the dpp and d mu, for example. And this is just the delta function. This is k-perp and k-parallel. And this new function from our work would argue that you actually have much stronger in this cross-looking regions where you get a lot more power from those two bands, both along the k-parallel equals 0 and also along the k-perp equals 0 modes, the directions where they pick up stronger interaction. And now if you couple that with the spatial turbulence model, you can try isotropic models, which is, say, for fast modes, that's been shown by Alice's group 20 years ago, and many other groups also. And you go back to the space folk solar wind models with 2D plus slab. Again, they have the 2D plus the parallel propagation modes. Or Goresh radar would have most of the power concentrated near k-parallel equals 0 and finite k-perp modes. And you multiply this with the new either the delta function, the new models, and we generally find that the scattering rate d mu got quite a bit larger, and depending on which parameter regime for the cosmic ray energy, also I'm personally more interested in getting them applied to the jet regions where we can get the particles accelerated to much higher energy, and we do find that the much slower diffusion coefficient rates are coming from the fact that the time decorrelation has this feature rather than the delta function. So the third implication, sorry. So first implication was this new time decorrelation function. The second implication is that the cosmic ray transport is gotten a lot slower. The third one is actually because all the satellites can actually measure the density fluctuation, and so there is kind of a mini debate, I would say, because there is a dominant, nearly incompressible model in the space community looking at density fluctuation scaling as a function of Mach number. But if you use this new time decorrelation function with the turbulence, even with 2D plus slab, we actually get delta overall goes like Mach number to the 1 power, which is something that Cho and Lazarian back in 2003 using linear theory has already predicted. And it turns out we teamed up with Bill Marshall's group, and they look at the first 8 orbits of Parker data, and this is so distance to the sun. So the Parker goes out to about 20, right now about 20-ish solar radius away. And the top panel is the density, but the density divided by its mean, this is the green curves, actually stay roughly flat, varies between 10 to 20%, 0.1 and 0.2. And the beta does drop down with a mean beta 1 drop down to about 0.3-ish. And the turbulent Mach numbers stayed around 0.4-ish. And sometimes you do go to transonic. This is one of the reasons I got it, that they actually can measure transonic turbulence in situ. And then we run a large number of compressible MHD simulation using their parameters for different betas and different cross helicity and different equation of state. And the bottom line seems to be that we almost consistently get delta rho scale as sonic Mach number linearly, which is something quite consistent with what the derivations I mentioned earlier. So just with the last minute, also, we're now moving towards the possibility of this is a 3D global using Asina++, Jim, and And we start from solar, kind of solar 1.01 solar radius going out to about 40. And we do injection, turbulence injection at the boundary and then expand the solar wind. We actually can do this kind of global simulation. The goal is trying to then compare with Parker data directly. And the initial runs seem to be quite encouraging. The dots, I apologize, I should put the dots are all from Professor Lingling Zhao from Huntsville. And then, and the curves, the color curves are from this 3D simulation. And we do get both the mean quantities, the wind speed and magnetic fields, as well as the fluctuation quantities all in the right region and with the right scaling. So that's quite exciting that we then want to use this to test the Z plus, Z minus evolution along the way. So to summarize, this kind of 4D FFT analysis allows us now trying to get the time decorrelation properties of MHD turbulence. And indeed, it turns out their functional form isn't quite as simple as some of the early. And now with this new kind of simulation, motivated and confirmed, fitted correlation function for fast and slow and RFIN modes. And we were able to then look at all the DPP, dmu, and the density, the transport coefficients and the density fluctuation. And the hope is then we'll be able to find its eventual role in the very high energy part where I think there's still a lot of unsolved questions there. Thank you.
Thanks, Hui. First question from James.
Really interesting. So am I understand this correctly? There are a buildup of low K, low frequency modes in your MHD simulations that do not follow any particular dispersion relation to waves. Is that correct?
Yes.
So are these undergoing a cascade? Do they participate in the cascade? What's their role in the turbulence?
So if you just look at the spatial, I didn't have a problem. If you just look at the spatial information, which, you know, ever since GS95, and space folks would argue go way back to the early 80s, the spatial, all the runs we do, spatial information look identical with any other runs. It's just when you start pulling out the frequency information, you find out they're all lying kind of cluster around this area. Yep, and they are very critical in cascade.
So what role do they play?
So that's another sort of the study. So you could argue all modes talk to them and then go on to their new K.
Okay, so there is a direct cascade that feeds on these low frequency fluctuation. Okay. Okay, thanks.
I just wonder what you see in the simulations of the solar wind, because it's the imbalanced turbulence, and there are a number of models. One of them was suggested by Andre and me, and whether there is a possibility of comparing.
Yes, so I don't know whether I had it in the backup slide. The way we set up the simulation, no, I don't. The way we set up simulation that we indeed intended is 100% imbalance, in the sense we try to do the inflow boundary condition. So it's just 1Z. And then because this is a large gradient, and we do see the other Z minus develop. So the question, and then we see the cross-collicity evolution. So that's one of the goals, is to figure out what are the mechanisms that are causing this generation and why it saturates at a certain level.
Do you have in the simulations fluctuations of density?
Yes. In fact, what you see, I can't tell. This is probably velocity. I have another movie that's showing the density, and this density variations here is called, the lines are coming from the simulation. The dots are from the Lingling's analysis of the solar wind data. Yeah.
Would be interesting to see the case pointers to this area.
It's one of the primary goals, yeah.
Next, Greg.
So very nice talk, Hui. And you covered a whole lot of stuff, but I wanted to address the question he just asked a little bit. those results don't actually imply that there are non-wave-like fluctuations. That low-frequency stuff is, I mean, those solutions, the reason why those curves all match nicely with slow, alphane, and fast is because they are all waves, but they're damping. And when you Fourier transform a wave, if you have just a single wave that's undamped, you Fourier transform, you get a delta function. If you take a wave that damps its amplitude and time in Fourier transform, it broadens out into exactly that form. So that's the form that he's fitting. So it doesn't mean that these are not the MHD waves. It means that the nonlinear transfer, which is taking the amplitude of a wave of some, you know, like you think about a wave packet, and it's interacting and it's transferring its energy to other scales, and its amplitude is decreasing. You Fourier transform that in time, and you get that broadening. And so all that low frequency stuff is waves. It's the broadening because those waves' amplitude is changing in time. So that's actually what is really happening there in terms. So when you said how do they participate in the cascade, they are the waves that are being cascaded as you are sort of evolving your simulation.
So we should debate about this. I think I mean there's definitely damping. I mean there's you can call it cascade also, which is a form of damping for that particular mode. But one of the things like I emphasize that there are 4 roots is that it's not the simple damping that one can write down. So there's a question of how much is just due to the damping, how much there's other interaction going on. So that's a question we don't know the exact answer yet, but we think it's more than that. Yeah.
Next one is Beta.
Yes, my question is in this line about this damping effect, because this may affect high energy particles, right? And transport. So do you have any inference of the diffusion coefficient from?
Yes. I didn't show the final plot partly because we're still debating over it, but all the cases we found the d mu can get orders of magnitude higher. So and particularly for high energy particles where
higher with respect
to using say a delta function in decorrelation function or some other like simple Gaussian Lorentzian.
Right.
That's partly I was also answering Greg is that this numerical nonlinear function form turns out it does have its nuance that it does make a big difference in high energy transport, high energy particle transport.
Yeah, this is interesting.
Okay, a final question by Axel.
Your K omega diagrams. Have you ever seen power way above the diagonal? And I wonder whether that is potentially an artifact if one did see that.
Way above diagonal?
Yes. You didn't see that. I was just wondering from your experience, did you ever...
When you say diagonal, you mean...
yeah, look at one of the projections that's here. Yes, exactly. So where you write on the left, for example, fast or...
Oh, you mean this?
Right.
Yeah, yes, is this what you mean?
Yes.
This is from driving.
Yes, I see.
So
artifact,
yeah, I forgot to mention in our analysis, when we count, there are several papers, when we count how to differentiate different modes, we cover all the driving region, both in omega and in K, because you're driving it. So we leave those out and we then count the rest of it. Yeah.
So that's driving violates causality.
It's violates causality.
Right. Yeah. Thank you.
Okay. Well, we have to go somewhere. Yeah.
One.
I'll just mention, as it's related to this, and actually it might be one of the papers that started this, is that curve, I mean, when you said it violates causality, when we drive our kinetic simulations, we are actually driving it with that curve, which is that Lorentzian curve. Our driving is exactly fit by that curve. And so it really is a wave driving where the amplitude and phase of the driving waves is drifting, and that's what causes the broadening of that from a delta function into that Lorentzian curve. I mean, that's actually sort of what I think started this whole process. It's a 10 barge and Howes and Hammett, and there might be one other author, Dorland, 2014 paper. We call it oscillating longevity antenna. Yeah.
Okay, thanks, Sam, again. So we will have a break, 30 minutes, and then we will reconvene with the next talk at 11.